dr. 2 pi dr is only a length, I need an area. 2 pi what?
2 pi rdr.
2 pi r dr. Right? 2 pi r is the circumference, a circle. Dr is the thickness. So now this replaces my differential area. Do you get it? So this is the first step in using continuity. And what the problem asks is, hypothetically, if I would come up with an average velocity that will call it U average, or U bar, that will have passed the same mass flow rate as this previous diagram. What will be the U average? In other words, when you do this integration from continuity, if I want this to be equal to rho, V, and an A, where now I have a hypothetical uniform velocity to take care of this non-uniform profile. What will be that average velocity? Do you understand the statement of the problem? And I'll give you the answer, because this problem is by far non-trivial. So the intermediate step is the average velocity when you go through the integration. As the intermediate step is half the maximum velocity at the center, and that's given in the problem statement. So that's the first step. Find out, prove to me that based on continuity, the so-called average velocity is happen to be half the maximum velocity. So let me pause and make sure you understand what is being asked. Yes?
So for the m dot equation, why is it little r and not big R?
The big R is, oh, sorry, I did mess up, thank you. So this I meant to be small r, thank you. The cap R is the actual radius of the whole height. Yeah, this should be small r, thank you. So please correct that in your notes. Yeah?
What is the sub C of the U there again?
This is the center line velocity, and you will see that in the problem statement. Which happen to be also the maximum. So the problem gives you the velocity distribution as a parabola, as a function of radius squared. Yes?
Is that formula only applicable when it's a parabola like that?
Which formula? This one?
Yeah.
This is absolutely correct. It's a function of the shape of the velocity profile, which given the problem statement is a parabola. Yes. Right. If it's linear, it's different. Linear meaning if I give you a different problem, and just say the velocity go like this, then you have a different answer. Yeah, it's absolutely correct. Do you understand part one? Okay, now part two, which is the real gut of the problem, is to do the same type of analysis now for momentum. So this is part A for continuity. Now how would I extrapolate and look at, in the first case, assuming I call it MF, momentum flux. At first, pretending that the flow at uniform velocity of U average, momentum flux is what times what? Product of two things. M dot U, thank you. M dot U. So what this asks you to do is pretend, just pretend for a moment that I have the average velocity so that I can calculate a momentum flux by hypothesizing or assuming that the velocity is uniform. And I will get this answer. You follow? So this is kind of the companion of this so-called average velocity. But in reality, the actual momentum flux, where I have to account for non-uniform velocity distribution, I will have to integrate, just like I did with continuity. Okay, the integration consists of integrating the velocity, momentum flux, velocity times the mass flow rate. And what that translates to will be the same thing I did for continuity, replacing the d mass flow rate with rho u dA. The added term to get momentum flux is I have to multiply the m dot by the velocity. So now the integration becomes a little bit more complicated. Yes?
In the non-uniform momentum flux equation, why is it not u bar and it's just u for velocity?
Because here I do have to account for the velocity in the actual profile, whereas in the uniform case, I see why I'm confused. That would be make it better. So in the uniform case, I'm pretending that the flow is now represented by this uniform velocity. So for my uniform hypothetical case, I have this answer. The real life non-uniform case, I have this answer, which require a more elaborated integration. You have now u squared. Okay? And the question asks you, how are they different? Which one is greater? By how much? And what this exercise will set the stage for is later on in some other homework, they allow us to deal with non-uniform problems, which is always the case in real life. In chapter 8, in a month, when we deal with flow internal to pipe, this is what we're dealing with. This is hypothetical. But this makes our life a lot easier, right? I can do the problem in 5 minutes if I assume uniform velocity. If every problem I have to assume this profile will take me an hour. But the question for engineer is, when you do this assumption, how much is your answer off? And that's what this is asking you to do. Yes?
So they don't give us equation of the velocity profile in terms of r, maximum value, but they don't give us u of r.
Okay, let me just give you the velocity profile since this has been asked more than once. So in the problem statement, you are given this parabolic square velocity distribution as a function of the radius. And UC is the center velocity. How do I know? Well, when radius is 0 at the center, I get UC, which happens to the maximum. When this is capital R, what is the velocity at the wall? 0. Why? Low slip. So this will influence the answer because you have to integrate that. Right? So it's a lot of explanation. I spent 10